Hi everyone, in this video I want to talk about how to work with samples inside Opusmodus via SuperCollider. Now, if you're new to SuperCollider, working with recorded audio can be a little bit more tricky than using regular synths with saw oscillators and squares and stuff like that, mainly because there's many different methods available to actually manipulate recorded sound. So that's what I want to go over in this video. I want to take a look at the different methods and show you what you can do with the different UGens, unit generators, that are designed to work with samples. Before we do that though, I have a score here which has a regular synth sound, which I showed in another video. We're not going to go over that. And we have our sampler right here, which uses a sample. So if we play this score, you can hear that we hear the vocal sample together with some chords, a regular synth. Let's listen to that. Right, I will not play the whole thing because we have a lot to go over. But let's take a look at the top of the file here, where we do the very first thing that you would want to do if you want to work with samples, which is actually load the sample. And you load the sample in a buffer. Now, buffers are used with all the different sampling methods inside SuperCollider, as well as some other methods. They're very useful to know about. If you want to know more about them, I would advise checking out the SuperCollider documentation. In case you're wondering why I have this on the side here, if you go to the SuperCollider documentation online and you right click and you say save as, and you save this as HTML, you can then save it in your documents folder, and then it will show up here, and you can just right click and open it in a new assistant. This will allow you to browse the help documentations, which can be very useful. So if we go to UGens here and we go to buffer, we can see that we have a lot of different methods available there. And so if you click on one of them, for example, buff read, you can see the arguments that it takes. You can see some examples, which are of course in SuperCollider code, but it should still be like very useful. So that's the first thing we do. And I'm showing actually two different methods here. So the first one, it just loads a single sample and it sets it to this variable right there. I used the pitch in the variable name. And this method below is the same. But I also here have a method to load multiple samples. So this Vox loops directory, it holds multiple loops, and if we loop over that, we can collect all of them into a buffer. So this will actually create a list, a regular list filled with these different buffers, these SuperCollider objects. So we can then access those using list indexing. So for example, if we want to use just find the first one in there, we use our nth method 0, and then we provide the list. If I want to have the second sample, I would do this, right? So it's pretty straightforward. I like to use this for drums, for example, when you have multiple hi-hats in a folder and you want to select different variations on those. This can be much faster. So that's for loading audio files. Then below that is a slightly off topic, but something I just wanted to show because I haven't showed it yet. Below that we have a reverb effect, and the sample synth in this score actually goes through that reverb effect. Now the way that works in SuperCollider is like this is a synth, right? You say SC, you call the def synth, you give the name, blah, blah, blah. We do the same thing when we're working with effects. It's still a def synth. The only difference here is that it would need some sort of input. So what we're doing is we're using the in.ar UGen, which can read from a bus, and then that's the signal that we're working with. So in order to do that, we first need to create that bus. So we create an audio bus. We can also create control buses for modulation. I will go over that in another tutorial. So we can create an audio bus with 2 channels and we give that a name. So now when our reverb synth is being created, what happens is that it reads from that bus. So everything that goes to that bus is then the input of the effect right here. So let's just actually launch that. I think I messed something up somewhere. Oh, yeah, here. Right, so that's a reverb synth. And now when we have a regular synth, we can set the output of that to our reverb bus. So in this case, if I create this synth, it will push it to the server. It will start playing right away, but the out argument is set to the reverb bus. So it will go out to this bus, and then the reverb synth is reading from that bus. Now, of course, in order to do that, we first need to create that synth as well, and just let it live on the server. And then let's listen to that. Make this a little bit lower. Not that low, maybe. So you can hear that it goes through the reverb effect, whereas if I set this to 0, it will go to my main output. So that's very quickly and briefly how you can use effects in Super Collider. So don't forget to also create the synth for the reverb, because it does need to be on the server, of course. So we have that, and then below that we come to the thing that I actually want to explain, or one of them at least, which is our sampler. Now, in here we see some things that we're familiar with, such as an envelope, but we also see other things that we might be less familiar with. So let's focus on the signal line here. So here we use the UGen that's a very convenient one for working with samples. And let's actually find it, or actually we already have it here. So we can see that the first argument to this is the number of channels. So that I set this to 2. Then we get the buffer. Usually we initialize that just with a 0. So we can say buff 0, and then we specify that once we create the synth. And then we have a pointer. Now the pointer is important because this is what reads through the audio files. It's where you want to be in the file. So if you set this to a static point, you're always only going to hear that static point. It doesn't actually play through the file. It fixes it at a specific point in the file, so it doesn't automatically play back. So what we do in order to actually hear the sound is first we set a start point, which I've set to 0 right here. And then what we do is the second argument to line is so line just creates a linear shape. So the second argument to line is where it ends, and the third argument is how long the line takes. So we start at 0, we end at the total frames inside the buffer minus 1, because the first index is 0, so we need to actually subtract 1 to go exactly to the end of the buffer. And then what we do is we want to know the duration of the sound, and for that we can use the buff duration argument, and then we specify the buffer. This will know how long the audio file is. So what we now have is a line from 0 to the very last frame, and the speed of the line is set by the duration of the buffer. All of that you pass into the pointer argument, and this actually plays through the file. So you don't have to do this, but if you do this, you actually get this like the proper way to sample. So now let's evaluate this, and or rather, yeah, that, and then let's call it. So you can hear it, but one thing that might be confusing is that we have a note here that is set to 60, and if we change it, it actually works. So, and the way that works is what I'm doing is I have my rate by default set to 1, I think. Oh no, I don't even have a rate. I just have it right here. But what I'm doing is the total duration of the line that reads through the buffer is being divided by the rate. And to convert the note, the MIDI note, to a MIDI ratio, we use the MIDI ratio method. The whole deal here is that these buffers and these buffer playback methods, they don't work with frequency, and they also don't work with MIDI notes. They just work with rates. If we go back one level here and we have this play buff, for example, you can see the rate argument, and they say, okay, if you set it to 1, it's basically the original sample. If you set it to 2, it's 1 octave higher, to 0.5, an octave lower, etc. So it uses a ratio for that. So what we we need to do is we need to convert our MIDI note to a ratio, and that's what we're doing here. Now, the only thing I'm doing in addition to that is I'm subtracting 60, because the MIDI ratio, it expects that the note 0 is the original sample, and I'm actually passing in the actual MIDI note numbers. So that's why I'm subtracting 60 there, which is a little bit arbitrary. It depends on the, of course, on the pitch of your loop. So if your loop is in D, for example, you would use from memory, I think, note 64 to get it to root pitch. So you have to mess around with that a little bit. But that's what I'm doing right here. And by dividing the total duration of the line that reads through the buffer by the rate, I'm able to then control the actual pitch of it. So we can set it to 30, for example. Now, one thing you notice when I do this is that if we do this, because this is the length of the line that we create, just think of the line as an envelope, because this is the length of the envelope, we play back slower through the file if the rate gets lower. So you can hear, if I go with a higher rate, you can hear that it's much slower. So to deal with this, there are different methods that we can use. And for my purposes in this score, this buff read was actually enough. But in other scenarios, you might use something else. So let's focus on some other methods to work with sound. So first, I have an example here where I'm, instead of controlling the pointer of the buff read argument with a line, I'm actually controlling it with the mouse. Now this is a slightly more tricky function. Let's play it first. Let's analyze it. So what happens there is, instead of using this line, we use the mouse position to say where we want to be in the buffer. What we're also doing in addition to that is lagging this a little bit. So we have this lag UGen in SuperCollider, which slows down values that are coming in, and you can use this to prevent clicks, but you can also do it to set up pitch glides and stuff like that. It will just lag everything. So here in this synth, what we have is we have our buff read UGen again. We have 2 for the number of channels we want to use. Buff num here just to select a sample. Then the third argument of buff read, as you might remember, is the pointer. So in there we start with the lag UGen. In that we have this K2 UGen. This is a UGen very specialized. It converts AR audio rate to it converts control rate signals to audio rate. So these mouse UGens, they are control rate, meaning they don't go as fast. And this K2A, actually the name says it, converts that into audio rate, which is something that the lag UGen expects. So there's a lot of mess here just for some conversion. So, and then we can set the range here of motion. So I set it from 0 to 2. And then we can set for the lag time itself, I'm using 0.1 to 2. We can change this. We can, if we set it, for example, 2 to 5, and then I play this. You can hear if I do that, and if I slow down the mouse, or if I stop the mouse, you can still hear that it lags, basically. We can also do something like this to make that even more extreme. Right, so that's just one way to sort of show you how that whole pointer situation works. Instead of using the mouse for that, you can also use the sine oscillator so that it sweeps through the file back and forth. Right, so now we're with the sine movement, we're sampling through the file. Now here another method here is if you just want to have the most regular playback that always sounds like the original sample, you would use your pointer, which you would start at 0. You would then subtract 1 from the frames of the number of frames in the sample. So remember, this method calculates the number of actual frames, which we subtract 1 from, and then we have the full buffer duration. Use this one as a template as a starting point for just having full loops inside Super Collider. Just sounds like the whole loop. Now, if you would want to revert that, what you would do is you would set the starting point of the pointer to the last frame. So in this case, I'm using the buff frames there. You can see here I use this for the ending point, but here I use it for the start argument, which is the first argument of line. And then for the end, I specify 0. So now it goes from the last frame to the very beginning of the frame. Again, I divide that by rate to have control over the playback speed. And then at the end here we have the total duration still of the sound. Actually, in this case, probably I would remove the rate here. We don't need it, and we'll also make it a little bit simpler to look at. You can remove it here as well. So you can hear it's just a loop, but now it's being reversed. Now, with that out of the way, let's go to a more complex example, which is the granular synth. Like with all of them, the rate is bound to the pitch, which means that if we want to change the pitch, we also change the playback speed. Now, as you might know, in granular synthesis, what we do is we cut up an audio file in very small snippets called grains. And because of this, we can actually speed up the file without changing the pitch. So I have an example here where I have a synth with the grain buff UGen. And this, I know this looks very ugly, but just to make it readable for you, I want to have all the arguments named and on a different line. So let's first listen to this. Okay, not super exciting, but that's what it sounds like. And then let's take a look at these arguments. So what we're doing right here is we have the first argument of our grain buffer is actually the number of channels again, which is 2. The second one is a trigger, and this is going to trigger the grain. So I'm using a impulse UGen for that. You can use a lot of different things for that. Then we have the duration, which is the length of a grain. So the duration, a grain is usually quite short. We can make it even shorter like this, and we can increase the rate like this. And we can start to make it longer then. Let's make this one slower again. Let's go with a very slow rate here, but longer durations. So now you can hear that they start to overlap these grains. Right, so already with those, a couple of arguments, you have a lot of control or a lot of different sonic possibilities. Then we have the buffer as an argument, and actually let's find this grain buff in our buffer UGen so that we can look at the actual documentation. It's grain buff right there, so you can see here all the arguments that I try to map out here. So with the buffer, we have the rate, we have the position, and this is actually the position where it will be, where the grain will start. That's why I call it start position. So this one is an interesting one to play with as well, because it's where we are in the file right now, in the audio file that we're scanning through. Then interpolation, which is a pitch shifting algorithm. This has very little effect on the sound. The options here are 1, 2, and 4. I'm using 4, I believe, no, 1 I'm using. Then we have the pan. We have the buff envelope, buff num, which is the envelope of the individual grain itself, so the volume shape of each individual grain. And then we have max grains, which is set to the default 512. So with those arguments out of the way, let's take a look at manipulating some of these values. So let's set, for example, the rate to 0.5. Let's change the start point. I can make it shorter again. I can increase the rate a lot. In this case, the start pause will not matter that much. Right, so quite some cool things you can do with this. To demonstrate that further, I created a new version here of the same, but instead of fixing all these values to just one numeric value, I'm controlling the start position here with the X position of the mouse. The start position has a range of 0 to 1, I believe. The position 0 is beginning, 1 is the end of the file. So that's what I'm setting up right here. And then I'm also controlling the duration of the grain with mouse Y. So let's listen to that, and then we'll move the mouse around a little bit. And one thing you can hear is if the mouse stops, if I don't move it, then we're not going through the file anymore, but we're being fixed at one point, and that's when you start to hear that static tone. Now, to make the sound stereo, what I did here is I'm using a list for the impulse argument. So I'm creating grains at 2 different rates, and this will automatically be sent to the left and the right channel. So both channels trigger at a slightly different rate. Because of that, you can you can hear that difference in channels, which makes the sound stereo. I can make that more extreme. So now you can hear much more being generated in the right channel, assuming that I'm wearing my headphone the right way around. So that is a little bit about grain buffers. They're very interesting. One thing you really have to watch out for with these is that they won't work at all with stereo audio files. So if you load a stereo audio file and you try all of this, it will just silently fail, not give you any error message. So the way to deal with that is, well, the most obvious way to deal with it is to load a mono sample, which I actually usually name them mono now for this purpose. So if you use a mono buffer, which only has 1 audio channel, it will just work. Another way to work with that is to use the buffer read channel method. So rather than just buffer read, we're saying, hey, we want to read 1 channel of a buffer. In that case, this is a stereo file, but we say, okay, I only want to hear channel 0. I only want to hear the first channel. So if we then put this in our synth, it should still work. Let's try B2 here. Right, so that also works. Now, finally, because I know this, we're getting towards a long video and there's lots of information in this one, I want to show you just one fun method, which is where we create a small, simple synth, again, using the playbuff.ar. And let's first put that on the server. So this is pretty much all of the techniques that I've shown you. So then after that, I create this coin toss function, which basically compares a random number to the bias I provided. And if it's lower than that, it will say true. And if it's higher than that, it will say false. And then the bias, we actually we call this function right here. And we use this mixed probability and the total time. So what it will do is the mixed probability is an envelope, so it will have different values. Sometimes they're going to be below, sometimes they're going to be above the random number outputted by this function. And based on that, we use an if statement where if it's true, the first form gets evaluated, and otherwise the second one, which are in my case different buffers. So what that means is that we randomly get different samples when we're looping. And notice that I used a regular Lisp loop here. So let's listen to that. I can use some other synths for this as well, or other samples. So you can hear that it mostly favors the lowest sample here. Now, of course, you can combine all of this with the mouse X methods as well. You can combine them with other UGens or with Opusmodus functions that create shapes and curves, etc. So you can do a lot with all of this. I hope this is enough to get you started with using buffers. If you have any questions, you can also always ask them here in the comments or on the Opusmodus forum. And then all that's left for me is to thank you for watching and yeah, see you in a next video.